particle physics. An atom, it consists of a centrally positively charged nucleus, and that is there in front of you. The blue colored one is what this is, a positively charged nucleus. And outside this nucleus, you have some shells, and within these shells, we have an orbiting electrons. So how do you describe the nuclei? You can see on the right hand side, we have a typical representation of an atom. The upper notation represents a nucleon number, and the lower notation, which is represented by Z here, it represents a proton number. So what is a proton number? It's very simple. It is the number of protons in a nuclei. What is a nucleon number? The total number of neutrons plus protons in a nuclei. So remember, when we're going to talk about the nucleon number, we mean it's neutron plus proton. So there is a little bit of more explanation for these subatomic particles. And these are the few things which you should remember as well. So first of all, you should know that the proton has a charge of about 1.6 times 10 raised to power minus 19 coulombs, and the neutron is a neutral thing. It's a neutral subatomic particle. So therefore, it has zero charge. If you talk about the electron, it has a charge that is equal but opposite to that of the proton. So it's minus 1.6 times 10 raised to power minus 19. And if you talk about the relative charge, the proton has plus 1 charge, neutron has 0, and definitely electron has a minus 1 relative charge. Then let's talk about the masses of these subatomic particles. The proton has 1.6 times 10 raised to power minus 27. Neutron has 1.675 times 10 raised to power minus 27. And the electron has 9.11 times 10 raised to power minus 31. And you can see from these masses that the protons and neutrons are a little bit heavier as compared to the electrons. So this data which is there in front of you, actually this is given in the data sheet as well for all of the A-level boards, but you also have to learn these ones. So I know that if a good physics student learns all the charges, relative charges and the masses, definitely it will be really helpful for them to attempt few questions in the exams. The next topic is about isotopes. So isotopes are the elements which are having the same proton number, but they are having a different nucleon number. So we have read about the proton number and nucleon number before. So that means if something which has the same proton number but a different nucleon number, and nucleon number is what? Nucleon number is proton plus neutron. So if the proton number is same, where is the difference in the isotopes? The difference is in the neutron number. So definitely two isotopes, they are going to have the same proton number, but they are going to have a different neutron. So therefore, they are going to have a different nucleon number. And so example is there in front of you, uranium-238-92 and uranium-235-92. So in uranium-238, the proton number is 92, and in 235, the proton number is again 92. So the difference is in the neutron number. So the neutron number 238 minus 92, that is 146, and for 235 minus 92 is 143. So this is the difference. One is having a neutron of about 146 and other is having a neutron number of about 143. Similarly, we are having few isotopes of hydrogen, which among them is hydrogen simple, which is called as 11. Then there is deuterium and there is tritium. All of these three hydrogen elements, they are having the same proton number, but deuterium is going to have 1 neutron and the tritium is going to have 2 neutrons. And this is the difference between two of them, but they are the isotopes of each other. So, next concept should be about the stable and an unstable nuclei. So, there are a few differences which you should remember about the stable and unstable nuclei. And I have a separate video about why we call a nuclei as stable and why do we call a nuclei as unstable. So, first of all, the difference between a stable and nuclei stable about the aspect of radioactive decay. A stable nuclei, it does not undergo a radioactive decay, but an unstable nuclei, it always undergoes a radioactive decay. Why? Because it needs to get stable. So therefore, an unstable nuclei undergoes a radioactive decay. Then the proton to neutron ratio. In stable nuclei, the proton and neutron ratio is the same. But in unstable nuclei, there is an imbalance in the ratio of the proton and neutrons, and therefore, this is the reason they are called as an unstable nuclei. Then about the energy state. In the stable nuclei, they are energetically very favorable and they are very stable. But as compared to this one, the unstable nuclei is energetically very unfavorable and it is not stable. The examples of a stable nuclei is carbon-12 and oxygen-16, and the unstable nuclei example is uranium-38, which you will see in the further studies as well, that uranium-232 is very famous for emitting out the radioactive radiations. So as you have just studied that an unstable nuclei will undergo a radioactive decay to become stable. So let us go over what type of decays does it undergo. The first is the alpha decay. Alpha decay is when an unstable nuclei, it emits an alpha particle. Now what is an alpha particle? An alpha particle is actually a particle which consists of 2 protons and 2 neutrons, and if we see this in the periodic table, we come to know that this alpha particle is actually a helium nuclei. So here is an example here below in front of you that is about radium-226. Okay, it undergoes the alpha decay. So therefore, we will emit out what? We will emit out 2 protons and 2 neutrons, that we are going to emit out helium. So if you just see this one, the radium, it undergoes to radon, right? And it emits out helium. The total number of protons before was 88, and after it's again 88, because if you just add up 86 and 80 plus 2 from the helium, but definitely the 2 of the protons have gone out from the radium. So therefore the identity of radium has definitely changed. Now it's a new nuclei which is radon. And that is why whenever there is an alpha decay, we are going to end up with a new type of a element. Why? Because definitely when the proton number changes, the identity of a nuclei also changes, and therefore this is what which is happening in the equation which is there in front of you. Next is a beta decay. In a beta decay, a neutron is converted into a proton, and this emits out an electron. Okay, so when a neutron is converting into a proton, definitely our atomic number will increase by 1. But since we are just converting one neutron to proton, but the total number of subatomic particles within the nuclei are remaining the same. This is just a change from neutron to proton within the nuclei. So therefore, although our atomic number increases by 1, but our mass number remains unchanged. So you can see here, example below, that this is an example of carbon 6. The total number of nucleon before was 14, and even after it emitted the electron number, the total number of nucleon remains the same. But you can see that the proton number has changed from 6 to 7. So that is why this element is now not carbon, and now it is a nitrogen. So this is something which is also known as the decay of the carbon. So now let's talk about the fundamental particles. Fundamental particles are a very important concept. Remember, they appear to have no structure and they cannot be broken down into smaller pieces. So our universe consists of 3 fundamental particles: up quark, down quark, and an electron. After fundamental particles, you should know about the fundamental forces. There are 4 fundamental forces: the electromagnetic force, the strong nuclear force, weak electromagnetic force, and the gravity. This table actually gives you an overview about these fundamental forces. Actually, let us first of all see these fundamental forces in detail, and then we will come back. Okay, now the first force is the electromagnetic force. Electromagnetic force is actually the force between the everyday objects, and it's actually a force which is present due to contact. So the exchange particle, it is the photon definitely, and they actually act over an infinite distances. But remember, the strength of this force, it decreases with how much? With inverse square relationship to the distance. So that means this force is going to decrease by times of 4. That means 1/4. And the photons which are created during the electromagnetic interactions are actually the virtual photons. Okay? Why we call them virtual photons? Because they are not actually really present every time, but they are present only during the time of interaction. As you can see in this figure here, you can see that the strength of this force decreases by the inverse square relationship. What does it mean? That as the distance between two oppositely charged particles doubles, the force reduces by factor of 4. And the strong nuclear force is actually a strong interaction between extremely short range. And this is typically about 10 raised to power minus 14 to 10 raised to power minus 15 meters. This force is acting where? It is acting between quarks, and remember the exchange particle in the strong nuclear force is gluon. Okay, and it is very high magnitude. It is about 137 times larger than the electromagnetic force. 137 times larger. So this is one of the strongest forces to exist. Then comes the weak force. The weak force is about million times weaker than the stronger nuclear force, and it also acts over an even shorter range, that is typically about 10 raised to power minus 18 meters, is actually just 0.1% of the diameter of the atom. This force is actually responsible for beta minus and beta plus radioactive decay. Then comes the fourth fundamental force, which is the gravity. Okay, so gravity, if you remember, it's the fundamental force that drives the behavior of the universe. Okay, gravity is one of the weakest of all the four fundamental forces, which is typically about 6 times 10 raised to power minus 39 of the magnitude of the strong force. And it's actually macroscopically, if you say, the gravitational theory works very well. Okay, so if you just see what is the exchange particle in gravity, it's the graviton. Okay, and if you see on the quantum scale, the graviton would be almost impossible to observe due to the extremely small magnitude of the force of interaction. Then comes photon model of electromagnetic radiation. It says that an atom absorbs and emits radiation in discrete amounts. And there is a typical equation for this one, which is called as Planck's equation, which says E is equal to hf. E stands for energy, H stands for the Planck's constant, and F stands for the frequency. Now this Planck constant has a value of about 6.6 times 10 raised to power minus 34 joules per second. Actually, it was a scientist whose name was Planck, okay, who actually called these discrete units of energy quanta, and then these small packets of electromagnetic radiations were then called or became to known as photons. Okay, now another concept is about annihilation. Annihilation is when the particle and an antiparticle interacts with each other. Okay, and when these interact with each other, the total mass of the particle pair is converted into energy. And which types of energy? In the form of two gamma ray photons. So for example, a proton and antiproton annihilate, they will give a 2 gamma ray photons. And similarly, if an electron and positron, which are both, one is particle and positron is an antiparticle, if they interact with each other, which is called as annihilation, they are going to emit a 2 gamma photons. So remember, whenever there is a particle and antiparticle annihilation, there is an emission of 2 gamma photons. And the total energy of the gamma photon is equal to the total rest energies of the particle. And this is, why is it possible? In order to conserve the energy. last one, which is called as pair production. What is pair production? Pair production is a concept which is just opposite to that of annihilation, which we have studied just now. So in annihilation, there was an anti-particle interaction giving out 2 photons. But in pair production, we are going to have a photon with an enough energy which can interact with a large nucleus, and then it will be converted into a particle and anti-particle pair. The rest energy of an electron is about 0.51 mega electron volts, or we can say it's 8.2 times 10 raised to the power minus 14 joules. And in order to create the particle and anti-particle pair, this photon, remember, should have enough energy to create both the particles. So therefore, the wavelength of the photon can be calculated by this equation which is there in front of you. Energy is equal to hc over lambda. C is the speed of light, h is the Planck's constant, and E is energy, and lambda, for example, is the wavelength. And using this formula, you can calculate the wavelength, and definitely you can rearrange this formula for whatever the question is coming up in the exam to calculate the energy, or sometimes they ask you to calculate the wavelength of the photon as well.
Tutoring and resources, log on to www.physicsonlinetuition.com.